Today we are looking at a diagnostic playbook specifically for you, the operators. Our goal is simple to extend the life of our blast furnace 2 years. This is not just about a technical specifications, it's about identifying anomalies early, isolating why they happen, and executing countermeasures that keep our furnace running longer and more efficiently. So if you look into the next slide, which is about the compounding thermodynamics cost of tuyer failure, which is a very sensible issue and this need to be addressed well. Otherwise, we operators could not able to catalyze ourselves, our initiatives, disciplined our initiatives. So all this is required, and for addressing all these issues, the second slide is full of those contents. So why is this priority? Now question arises that why that is having a priority. So because a damaged wear is never just a hardware failure, it's a critical disruption to the furnace thermal stability. It starts with localized damage but quickly compound into unplanned stoppages, suspended hot blast, and wasted coke. Each failure can cost huge and it can cost up to 2 to 8 hours of production, leading to severe spike in cost per ton. So our deliverable today is to break this cycle, and for that our third slide, which is about anatomy of a defects, that is about the damage radar. So if we look into this slide, these basically address towards fixing the problem. We have to know where to look. Data shows that primary danger zone is the tuyer nose, which faces the highest thermal overload from dripping hot metal and liquid slag. We typically see two types of defects: crack spanning weld joints from the thermal cycle and ruts or holes caused by the sustained liquid metal flow. By focusing on these specific zones, we can better predict failure patterns. And for that, our internal diagnosis is must. And this is with respect to dead water effect. So, as you know, the many failures start from the inside. In a standard design, a dead water zone can form where cooling water becomes static. This water boils against the hot copper participating and precipitating a massive insulating layer of lime scale. This scale acts as a thermal blanket. The uncooled copper tip then overheat, leading to rapid crack propagation. The deliverables here is understanding that internal cleanliness is just as vital as external condition. And in order to understand our next slide, which is addressing on external diagnostic, that is the permeability and channeling. Externally, the biggest threat is poor hearth permeability. When the dead man becomes impermeable, liquid hot metal and slag cannot drain properly and instead channel directly down the furnace wall onto the tuyer tip. This causes catastrophic film boiling where the external heat transfer vastly exceed our internal cooling capacity. In short, a healthy furnace floor protect the tuyer, and for that our subsequent slide is addressed on advanced diagnostic, that is the pro failure signature. Now if we look into uh, all these, as we know, we do not have to wait for a leak to know there is a problem. We use two types of vital signs: short term thermal detection spot, localized 500 degrees centigrade spikes at the 6 o'clock position, often occurring seconds before a crack; long term optical monitoring track physical erosion and bulging over month. These allow us to predict structural compromise before a leak even occurs. And for that, the hardware uh, countermeasure is going to address, especially with respect to the spiral cooling integration. So, if we look into our primary hardware deliverables, which is the spiral cooling tip, unlike legacy design that allow dead water zone, the spiral design forces intense water turbulence exactly where hot metal dripping occur. This maximizes the heat transfer and permanently eliminate the internal dead zones we discussed earlier. It is our most effective engineering shield against the thermal overload. So now coming to our operator's playbook, as you can see about heat and permeability. So as operator, our shield is how you manage these three gases. Target 1. Keep hot metal temperature strictly under 1500 degrees centigrade to protect coke porosity. Target 2 is maintain a stable blast pressure. Sudden drop can indicate uneven burden sinking. Target 3 is ensuring high voidage in the deadman for efficient drainage. Keeping these in the green zone is your first line of defense. So, what is our next slide, which is about a operator's playbook, that is slag conditioning and fluidity, which is supposed to be have a huge role in executing these all anomaly perfect online and keep the furnace stable. So slag chemistry is our second line of defense. We must maintain silica by SiO2 ratio strictly below 2. Higher ratio correlate directly with Tuyere failure. Physically, we need to maintain low viscosity and constant tapping. Remember, poor slag chemistry equals high viscosity, which leads to a catastrophic liquid channeling we saw earlier. So, coming to our the ultimate slide is on the 2-year life extension synthesis. So we can say that or to box up to wrap up the final deliverables is mindset shift. That is, 2-year life is not dictated by the copper jacket alone. It is the ultimate indicator of total furnace health. By combining high quality burden input, a stable permeability that is operational, and a spiral cooling that is related to hardware, we achieve our goals: zero liquid channeling and an extended 2-year life cycle. So let's use this playback to and that is playbook to keep the furnace stable and hot metal flowing.